Chapter 10. High Frequency, High Power and Nanoelectronic Devices. Objectives. 1. Understand how tunneling, transit time effects, and electron transfer can lead to NDR. 2. Understand silicon-controlled rectifiers. 3. Describe how insulated gate field effect transistors switch power. 4. Advances in a few nanoelectronic logic and memory devices. The diodes and transistors we have discussed thus far constitute the vast majority of semiconductor devices. However, there are a number of specialty devices that deserve our attention, and novel devices and materials can form the basis of future applications. In this chapter we describe two types of negative conductance devices, with applications in high-frequency circuits. Then we will discuss the semiconductor-controlled rectifier, SCR, an important switching device which can handle large amounts of power. Finally, we will consider new materials and device applications which depend on some very interesting extensions of the physics of materials we used in previous chapters. These new materials and new applications of physics will likely form the basis for the electronics of the future. The tunnel diode is a p-n junction device that operates in certain regions of its current voltage characteristic by the quantum mechanical tunneling of electrons through the potential barrier of the junction. See sections 2.4.4 and 5.4.1. The tunneling process for reverse current is essentially the Zener effect, although negligible reverse bias is needed to initiate the process in tunnel diodes. As we shall see in this section, the tunnel diode, often called the Eseki diode after L. Eseki, who received the Nobel Prize in 1973 for his work on the effect, exhibits the important feature of negative resistance over a portion of its current voltage characteristic. Degenerate semiconductors. Thus far, we have discussed the properties of relatively pure semiconductors. Any impurity doping represented a small fraction of the total atomic density of the material. Since the few impurity atoms were so widely spaced throughout the sample, we could be confident that no charge transport could take place within the donor or acceptor levels themselves. At high doping, the impurities are so close together that we can no longer consider the donor level as being composed of discrete, non-interacting energy states. Instead, the donor states form a band, which may overlap the bottom of the conduction band. If the conduction band electron concentration N exceeds the effective density of states Nc, the Fermi level is no longer within the band gap, but lies within the conduction band. When this occurs, the material is called degenerate N-type. The analogous case of degenerate P-type material occurs when the acceptor concentration is very high and the Fermi level lies in the valence band. We recall that the energy states below F are mostly filled and states above F are empty, except for a small distribution dictated by the Fermi statistics. Thus, in a degenerate N-type sample, the region between EC and F is for the most part filled with electrons, and in a degenerate P-type sample, the region between EV and F is almost completely filled with holes. A p-n junction between two degenerate semiconductors is illustrated in terms of energy bands in Fig 10.1a. This is the equilibrium condition, for which the Fermi level is constant throughout the junction. We notice that EFP lies below the valence band edge on the P side, and EFN is above the conduction band edge on the N side. Thus, the bands must overlap on the energy scale in order for F to be constant. This overlapping of bands is very important. It means that, with a small forward or reverse bias, filled states and empty states appear opposite each other, separated by essentially the width of the depletion region. If the metallurgical junction is sharp, the depletion region will be very narrow for such high doping concentrations, and the electric field at the junction will be quite large. Hence, the conditions for electron tunneling are met, filled and empty states separated by a narrow potential barrier of finite height. In Fig 10.1, the bands are shown filled to the Fermi level for convenience of illustration, with the understanding that a distribution is implied. Since the bands overlap under equilibrium conditions, a small reverse bias, Fig 10.1b, allows electron tunneling from the filled valence band states below EFP to the empty conduction band states above EFN. This condition is similar to the Zener effect, except that no bias is required to create the condition of overlapping bands. As the reverse bias is increased, EFN continues to move down the energy scale with respect to EFP, placing more filled states on the P side opposite empty states on the N side. Thus, the tunneling of electrons from P to N increases with increasing reverse bias. The resulting conventional current is opposite to the electron flow, that is, from N to P. At equilibrium, Fig 10.1a, there is equal tunneling from N to P and from P to N, giving a zero net current. When a small forward bias is applied, Fig 10.1c, EFN moves up in energy with respect to EFP by the amount QV. Thus, electrons below EFN on the N side are placed opposite empty states above EFP on the P side. Figure 10.1 tunnel diode band diagrams and current voltage characteristics for various biasing conditions. A. Equilibrium, zero bias, condition, no net tunneling. B. Small reverse bias, electron tunneling from P to N. C. Small forward bias, electron tunneling from N to P. D. Increased forward bias, electron tunneling from N to P decreases as bands pass by each other. Electron tunneling occurs from N to P as shown, with the resulting conventional current from P to N. This forward tunneling current continues to increase with increased bias as more filled states are placed opposite empty states. However, as EFN continues to move up with respect to EFP, a point is reached at which the bands begin to pass by each other. When this occurs, the number of filled states opposite empty states decreases. The resulting decrease in tunneling current is illustrated in Fig 10.1d. This region of the current voltage characteristic is important in that the decrease in tunneling current with increased bias produces a region of negative slope, that is, the dynamic resistance dV/d is negative. This negative resistance region is useful in oscillators. Figure 10.2 band diagram, A, and current voltage characteristic, B, for the tunnel diode beyond the tunnel current region. In B, the tunneling component of current is shown by the solid curve and the diffusion current component is dashed. If the forward bias is increased beyond the negative resistance region, the current begins to increase again, Fig 10.2. Once the bands have passed each other, the characteristic resembles that of a conventional diode. The forward current is now dominated by the diffusion current, electrons surmounting their potential barrier from N to P and holes surmounting their potential barrier from P to N. Of course, the diffusion current is present in the forward tunneling region, but it is negligible compared with the tunneling current. The total tunnel diode characteristic, Fig 10.3, has the general shape of an N. If a little imagination is applied, therefore, it is common to refer to this characteristic as exhibiting a type N negative resistance. It is also called a voltage-controlled negative resistance, meaning that the current decreases rapidly at some critical voltage, in this case, the peak voltage Vp, taken at the point of maximum forward tunneling. The values of peak tunneling current Ip and valley current Iv, Fig 10.3, determine the magnitude of the negative resistance slope for a diode of given material. For this reason, their ratio Ip/IV is often used as a figure of merit for the tunnel diode. Figure 10.3 total tunnel diode characteristic. Similarly, the ratio Vp/Vf is a measure of the voltage spread between the two positive resistance regions. The negative resistance of the tunnel diode can be used in a number of ways to achieve oscillation and other circuit functions. The fact that the tunneling process does not present the time delays of drift and diffusion makes the tunnel diode a natural choice for certain high-speed circuits. However, the tunnel diode has not achieved widespread application, because of its relatively low current operation and competition from other devices. In this section, we describe a type of microwave negative conductance device that operates by a combination of carrier injection and transit time effects. Diodes with simple p-n junction structure, or with variations on that structure, are biased to achieve tunneling or avalanche breakdown, with an AC voltage superimposed on the DC bias. The carriers generated by the injection process are swept through a drift region to the terminals of the device. We shall see that the AC component of the resulting current can be approximately 180 degrees out of phase with the applied voltage under proper conditions of bias and device configuration, giving rise to negative conductance and oscillation in a resonant circuit. Transit time devices can convert DC to microwave AC signals with high efficiency and are very useful in the generation of microwave power for many applications. The original suggestion for a microwave device employing transit time effects was made by W.T. Reed and involved an N plus at P at I at P plus structure such as that shown in Fig 10.4. This device operates by injecting carriers into the drift region and is called an impact avalanche transit time, IMPATT, diode. Although IMPATT operation can be obtained in simpler structures, the Reed diode is best suited for illustration of the basic principles. The device consists essentially of two regions, 1, the N plus at P region, at which avalanche multiplication occurs, and 2, the I, essentially intrinsic, region, through which generated holes must drift in moving to the P plus contact. Similar devices can be built in the P plus at N at I at N plus configuration, in which electrons resulting from avalanche multiplication drift through the I region, taking advantage of the higher mobility of electrons compared with holes. Figure 10 for the Reed diode, A. Basic device configuration, B. Electric field distribution in the device under reverse bias. Although detailed calculations of IMPATT operation are complicated and generally require computer solutions, the basic physical mechanism is simple. Essentially, the device operates in a negative conductance mode when the AC component of current is negative over a portion of the cycle during which the AC voltage is positive, and vice versa. The negative conductance occurs because of two processes, causing the current to lag behind the voltage in time, 1, a delay due to the avalanche process and, 2, a further delay due to the transit time of the carriers across the drift region. If the sum of these delay times is approximately 1/2 cycle of the operating frequency, negative conductance occurs and the device can be used for oscillation and amplification. From another point of view, the AC conductance is negative if the AC component of carrier flow drifts opposite to the influence of the AC electric field. For example, with a DC reverse bias on the device of Fig 10.4, holes drift from left to right, in the direction of the field, as expected. Now, if we superimpose an AC voltage such that decreases during the negative half cycle, we would normally expect the drift of holes to decrease also. However, in IMPATT operation, the drift of holes through the I region actually increases while the AC field is decreasing. To see how this happens, let us consider the effects of avalanche and drift for various points in the cycle of applied voltage, Fig 10.5. To simplify the discussion, we shall assume that the P region is very narrow and that all the avalanche multiplication takes place in a thin region near the N plus P junction. We shall approximate the field in the narrow P region by a uniform value. If the DC bias is such that the critical field for avalanche EA is just met in the N plus P space charge region, Fig 10.5a, avalanche multiplication begins at t equals 0. Electrons generated in the avalanche move to the N plus region, and holes enter the I drift region. We assume that the device is mounted in a resonant microwave circuit so that an AC signal can be maintained at a given frequency. As the applied AC voltage goes positive, more and more holes are generated in the avalanche region. In fact, the pulse of holes, dotted line, generated by the multiplication process continues to grow as long as the electric field is above EA, Fig 10.5b. It can be shown that the particle current due to avalanche increases exponentially with time while the field is above the critical value. The important result of this growth is that the whole pulse reaches its peak value, not at P/2, when the voltage is maximum, but at P, Fig 10.5c. Therefore, there is a phase delay of P/2 inherent in the avalanche process itself. A further delay is provided by the drift region. Once the avalanche multiplication stops, VTP, the pulse of holes simply drifts toward the P+ contact, Fig 10.5d. But during this period, the AC terminal voltage is negative. Therefore, the dynamic conductance is negative, and energy is supplied to the AC field. If the length of the drift region is chosen properly, the pulse of holes is collected at the P+ contact just as the voltage cycle is completed, and the cycle then repeats itself. Figure 10.5 Time dependence of the growth and drift of holes during a cycle of applied voltage for the reed diode. A. xt equals 0, B. xt equal R/2, C. xt equal R, D. xt equal 3R/2. The hole pulse is sketched as a dotted line on the field diagram. The pulse will drift through the length L of the I region during the negative half cycle if we choose the transit time to be 1/2 the oscillation period, that is, where F is the operating frequency and Vd is the drift velocity for holes. Therefore, for a reed diode, the optimum frequency is 1/2 the inverse transit time Vd/L of holes across the drift region. In choosing an appropriate resonance circuit for this device, the parameter L is critical. For example, taking Vd equal 10 million centimeters per second for silicon, the optimum operating frequency for a device with an I region length of 5 micrometers is F equal 10 million divided by 0.001 equal 10 billion Hz. Negative resistance is exhibited by an IMPATT diode for frequencies somewhat above and below this optimum frequency for exact 180 degrees phase delay. A careful analysis of the small signal impedance shows that the minimum frequency for negative conductance varies as the square root of the DC bias current for frequencies in the neighborhood of that described by EQ. 10.1. Although the reed diode of Fig 10.4 displays most directly the operation of IMPATT devices, simpler structures can be used, and in some cases they may be more efficient. Negative conductance can be obtained in simple PN junctions or in PIN devices. In the case of the PIN, most of the applied voltage occurs across the I region, which serves as a uniform avalanche region and also as a drift region. Therefore, the two processes of delay due to avalanche and drift, which were separate in the case of the reed diode, are distributed within the I region of the PIN. This means that both electrons and holes participate in the avalanche and drift processes. Microwave devices that operate by the transferred electron mechanism are often called gun diodes, after J.B. Gunn, who first demonstrated one of the forms of oscillation. In the transferred electron mechanism, the conduction electrons of some semiconductors are shifted from a state of high mobility to a state of low mobility by the influence of a strong electric field. Negative conductance operation can be achieved in a diode for which this mechanism applies, and the results are varied and useful in microwave circuits. First, we shall describe the process of electron transfer and the resulting change in mobility. Then we shall consider some of the modes of operation for diodes using this mechanism. The transferred electron mechanism. In section 3.4.4, we discussed the nonlinearity of mobility at high electric fields. In most semiconductors, the carriers reach a scattering limited velocity, and the plot of velocity versus field saturates at high fields, Fig 3.24. In some materials, however, the energy of electrons can be raised by an applied field to the point that they transfer from one region of the conduction band to another, higher energy region. For some band structures, negative conductivity can result from this electron transfer. To visualize the process, let us recall the discussion of energy bands in section 3.1. A simplified E-K band structure for gallium arsenide is shown in Fig 10.6 for reference. Some of the detail has been omitted in this diagram to isolate the essential features of electron transfer between bands. In N-type gallium arsenide, the valence band is filled and the central valley, or minimum, of the conduction band at K equals 0, normally contains the conduction electrons. There is a set of subsidiary minima at L, sometimes called satellite valleys, at higher energy, 3, but these minima are many carat above the central valley and are normally unoccupied. Figure 10.6 simplified band diagram for gallium arsenide, illustrating the lower, and upper, L, valleys in the conduction band. Therefore, the direct band gap at and the energy bands centered at K equals 0 are generally used to describe the conduction processes in gallium arsenide. This was true, for example, of gallium arsenide lasers, discussed in section 8.4. The presence of the satellite valleys at L is crucial to the gun effect, however. If the material is subjected to an electric field above some critical value, about 3000 volts per centimeter, the electrons in the central valley of Fig 10.6 gain more energy than the 0.3 electron volts separating the valleys. Therefore, there is considerable scattering of electrons into the higher energy satellite valley at L. Once the electrons have gained enough energy from the field to be transferred into the higher energy valley, they remain there as long as the field is greater than the critical value. The explanation for this involves the fact that the combined effective density of states for the upper valleys is much greater than for the central valley, by a factor of about 24. Although we shall not prove it here, it seems reasonable that the probability of electron scattering between valleys should depend on the density of states available in each case, and that scattering from a valley with many states into a valley with few states would be unlikely. As a result, once the field increases above the critical value, most conduction electrons in gallium arsenide reside in the satellite valleys and exhibit properties typical of that region of the conduction band. In particular, the effective mass for electrons in the higher L valleys is almost 8 times as great as in the central valley because of the smaller band curvature, and the electron mobility is much lower. This is an important result for the negative conductivity mechanism. As the electric field is increased, the electron velocity increases until a critical field is reached, then the electrons slow down with further increase in field. The electron transfer process allows electrons to gain energy at the expense of velocity over a range of values of the electric field. Taking the current density as QVdN, we see clearly that current also drops in this range of increasing field, giving rise to a negative differential conductivity dJ/d. A possible dependence of electron velocity versus electric field for a material capable of electron transfer is shown in Fig 10.7. For low values of field, the electrons reside in the lower valley of the conduction band, and the mobility, m equal Vd/e, is high and constant with field. For high values of field, electrons transfer to the satellite valleys, where their velocity is smaller and their mobility lower. Between these two states is a region of negative slope on the plot of Vd versus, indicating a negative differential mobility dVd/d equal O** for the actual dependence of electron drift velocity on electric field for gallium arsenide and indium phosphide is shown in Fig 10.8. The negative resistance due to electron transfer occurs at a higher field for indium phosphide, and the electrons achieve a higher peak velocity before transfer from to L occurs. The existence of a drop in mobility with increasing electric field and the resultant possibility of negative conductance were predicted by Ridley and Watkins and by Hilsum several years before Gunn demonstrated the effect in gallium arsenide. Figure 10.7. A possible characteristic of electron drift velocity versus field for a semiconductor exhibiting the transferred electron mechanism. O equal mobility in central, valley. OL equal mobility in satellite, L, valley. O** equal average magnitude of negative differential mobility during transition. Figure 10.8. Electron drift velocity versus field for gallium arsenide and indium phosphide. The mechanism of electron transfer is therefore often called the Ridley-Watkins-Hilsum mechanism. This negative conductivity effect depends only on the bulk properties of the semiconductor and not on junction or surface effects. It is therefore called a bulk negative differential conductivity, BNDC, effect. Formation and drift of space charge domains. If a sample of gallium arsenide is biased such that the field falls in the negative conductivity region, space charge instabilities result, and the device cannot be maintained in a DC stable condition. To understand the formation of these instabilities, let us consider first the dissipation of space charge in the usual semiconductor. It can be shown from treatment of the continuity equation that a localized space charge dies out exponentially with time in a homogeneous sample with positive resistance, Prob 10.3. If the initial space charge is q0, the instantaneous charge is, where Td equal Gs is called the dielectric relaxation time. Because of this process, random fluctuations in carrier concentration are quickly neutralized, and space charge neutrality is a good approximation for most semiconductors in the usual range of conductivities. For example, the dielectric relaxation time for a 1 ohm per centimeter silicon or gallium arsenide sample is approximately 1 picosecond. Equation 10.2 gives a rather remarkable result for cases in which the conductivity is negative. For these cases, Td is negative also, and space charge fluctuations build up exponentially in time rather than dying out. This means that normal random fluctuations in the carrier distribution can grow into large space charge regions in the sample. Let us see how this occurs in a gallium arsenide sample biased in the negative conductivity regime. The velocity field diagram for N-type gallium arsenide is illustrated in Fig 10.9a. If we assume a small shift of electron concentration in some region of the device, a dipole layer can form as shown in Fig 10.9b. Under normal conditions, this dipole would die out quickly. However, under conditions of negative conductivity, the charge within the dipole, and therefore the local electric field, builds up as shown in Fig 10.9c. Of course, this buildup takes place in a stream of electrons drifting from the cathode to the anode, and the dipole, now called a domain, drifts along with the stream as it grows. Eventually, the drifting domain will reach the anode, where it gives up its energy as a pulse of current in the external circuit. During the initial growth of the domain, an increasing fraction of the applied voltage appears across it, at the expense of electric field in the rest of the bar. As a result, it is unlikely that more than one domain will be present in the bar at a time. After the formation of one domain, the electric field in the rest of the bar quickly drops below the threshold value for negative conductivity. If the bias is DC, the field outside the moving domain will stabilize at a positive conductivity point such as A in Fig 10.9a, and the field inside the domain will stabilize at the high field value B. A small dipole forms from a random noise fluctuation, or, more likely, at a permanent nucleation site such as a crystal defect, a doping inhomogeneity, or the cathode itself, and this dipole grows and drifts down the bar as a domain. Figure 10.9 Buildup and drift of a space charge domain in gallium arsenide. A. Velocity field characteristic for N-type gallium arsenide. B. Formation of a dipole. C. Growth and drift of a dipole for conditions of negative conductivity. The formation of stable domains is not the only mode of operation for transferred electron devices. Nor is it the most desirable mode for most applications, since the resulting short pulses of current are inefficient sources of microwave power. Removal of heat is a very serious problem in these devices. The power dissipation may be 10 million watts per cubic centimeter or greater, Prob 10.5, giving rise to considerable heating of the sample. If the application does not require continuous operation, peak powers of hundreds of watts can be achieved in pulses of microwave oscillation. One of the most common applications of electronic devices is in switching, which requires the device to change from an off or blocking state to an on or conducting state. We have discussed the use of transistors in this application, in which base current drives the device from cutoff to saturation. Similarly, diodes and other devices can be used to serve as certain types of switches. There are a number of important switching applications that require a device remain in the blocking state under forward bias until switched to the conducting state by an external signal. Several devices that fulfill this requirement have been developed, including the semiconductor controlled rectifier, SCR. 5. These devices are typified by a high impedance, the off condition, under forward bias until a switching signal is applied. After switching, they exhibit low impedance, the on condition. The signal required for switching can be varied externally, therefore, the devices can be used to block or pass currents at predetermined levels. The semiconductor controlled rectifier is a 4-layer, PNPN, structure that effectively blocks current through two terminals until it is turned on by a small signal at a third terminal. We shall begin by investigating the current flow in a two-terminal PNPN device and then extend the discussion to include triggering by a third terminal. We shall see that the PNPN structure can be considered for many purposes as a combination of PNP and NPN transistors, and the analysis in Chapter 7 can be used as an aid in understanding its behavior. Basic structure. First we consider a four-layer diode structure with an anode terminal A at the outside P region and with a cathode terminal K at the outside N region, Fig 1010A. We shall refer to the junction nearest the anode as J1, the center junction as J2, and the junction nearest the cathode as J3. When the anode is biased positively with respect to the cathode, V positive, the device is forward biased. However, as the current voltage characteristic of Fig 1010b indicates, the forward biased condition of this diode can be considered in two separate states, the high impedance, or forward blocking, state and the low impedance, or forward conducting, state. In the device illustrated here, the forward current voltage characteristic switches from the blocking to the conducting state at a critical peak forward voltage Vp. Figure 1010 a two-terminal PNPN device, A. Basic structure and common circuit symbol, B. Current voltage characteristic. We can anticipate the discussion of conduction mechanisms that follows by noting that an initial positive voltage V places J1 and J3 under forward bias and the center junction J2 under reverse bias. As V is increased, most of the forward voltage in the blocking state must appear across the reverse biased junction J2. After switching to the conducting state, the voltage from A to K is very small, less than 1 V, and we conclude that, in this condition, all three junctions must be forward biased. The mechanism by which J2 switches from reverse bias to forward bias is the subject of much of the discussion that follows. In the reverse blocking state, V negative, J1 and J3 are reverse biased and J2 is forward biased. Since the supply of electrons and holes to J2 is restricted by the reverse biased junctions on either side, the device current is limited to a small saturation current arising from the thermal generation of electron-hole pairs, EHPs, near J1 and J3. The current remains small in the reverse blocking condition until avalanche breakdown occurs at a large reverse bias. In a properly designed device, with guards against surface breakdown, the reverse breakdown voltage can be several thousand volts. We shall now consider the mechanism by which this device, often called a Shockley diode, switches from the forward blocking state to the forward conducting state. The two-transistor analogy. The four-layer configuration of Fig 1010 suggests that the PNPN diode can be considered as two coupled transistors, J1 and J2 form the emitter and collector junctions, respectively, of a PNP transistor. Similarly, J2 and J3 form the collector and emitter junctions of an NPN transistor. Note that the emitter of the NPN is on the right, which is the reverse of what we usually draw. In this analogy, the collector region of the NPN is in common with the base of the PNP, and the base of the NPN serves as the collector region of the PNP. The center junction J2 serves as the collector junction for both transistors. This two-transistor analogy is illustrated in Fig 1011. The collector current IC1 of the PNP transistor drives the base of the NPN, and the base current IB1 of the PNP is dictated by the collector current IC2 of the NPN. If we associate an emitter to collector current transfer ratio with each transistor, we can use the analysis in Chapter 7 to solve for the current I. Figure 1011 two-transistor analogy of the PNPN diode. Using EQ 737b, with C1 equals Cn for the PNP, C2 equals Cn for the NPN, and with IC01 and IC02 for the respective collector saturation currents, we have. But the sum of IC1 and IC2 is the total current through the device. Taking this sum in EQ 10.3, we have. As EQ 10.5 indicates, the current I through the devices is small, approximately the combined collector saturation currents of the two equivalent transistors, as long as the sum C1 plus C2 is small compared with unity. As the sum of the alphas approaches unity, the current I increases rapidly. The current does not increase without limit as EQ 10.5 implies, however, because the derivation is no longer valid as C1 plus C2 approaches unity. Since J2 becomes forward biased in the forward conducting state, both transistors become saturated after switching. The two transistors remain in saturation in the forward conducting state. Variation of 5 with injection. Since the two transistor analogy implies that switching involves an increase in the alphas to the point that C1 plus C2 approaches unity, it may be helpful to review how alpha varies with injection for a transistor. The emitter to collector current transfer ratio C is given in section 7.2 as the product of the emitter injection efficiency I and the base transport factor B. An increase in C with injection can be caused by increases in either of these factors or both. At very low currents, such as in the forward blocking state of PNP diodes, I is usually dominated by recombination in the transition region of the emitter junction, section 7.7.4. As the current is increased, injection across the junction begins to dominate over recombination within the transition region, section 5.6.2, and G increases. There are several mechanisms by which the base transport factor B increases with injection, including the saturation of recombination centers as the excess carrier concentration becomes large. Whichever mechanism dominates, the increase in C1 plus C2 required for switching of the PNP diode is accomplished automatically. In general, no special design is required to maintain C1 plus C2 smaller than unity during the forward blocking state. This requirement is usually met at low currents by the dominance of recombination within the transition regions of J1 and J3. Forward blocking state. When the device is biased in the forward blocking state, Fig 1012a, the applied voltage V appears primarily across the reverse biased junction J2. Although J1 and J3 are forward biased, the current is small. The reason for this becomes clear if we consider the supply of electrons available to N1 and holes to P2. Focusing attention first upon J1, let us assume that a hole is injected from P1 into N1. If the hole recombines with an electron in N1, or in the J1 transition region, that electron must be resupplied to the N1 region to maintain space charge neutrality. The supply of electrons in this case is severely restricted, however, by the fact that N1 is terminated in J2, a reverse biased junction. Figure 1012-3 bias states of the PNP diode: A, the forward blocking state; B, the forward conducting state; C, the reverse blocking state. In a normal PN diode, the N region is terminated in an ohmic contact, so that the supply of electrons required to match recombination and injection into P is unlimited. In this case, however, the electron supply is restricted essentially to those electrons generated thermally within a diffusion length of J2. As a result, the current passing through the J1 junction is approximately the same as the reverse saturation current of J2. A similar argument holds for the current through J3. Holes required for injection into N2 and to feed recombination in P2 must originate in the saturation current of the center junction J2. The applied voltage V divides appropriately among the three junctions to accommodate this small current throughout the device. In this discussion, we have tacitly assumed that the current crossing J2 is strictly the thermally generated saturation current. This implies that electrons injected by the forward biased junction J3 do not diffuse across P2 in any substantial numbers, to be swept across the reverse biased junction into N1 by transistor action. This is another way of saying that A2, for the NPN transistor, is small. Similarly, the supply of holes to P2 is primarily thermally generated, since few holes injected at J1 reach J2 without recombination, i.e., A1 is small for the PNP. Now we can see physically why EQ 10.5 implies a small current while C1 plus C2 is small, without the transport of charge provided by transistor action. the thermal generation of carriers is the only significant source of electrons to N1 and holes to P2. Conducting state. The charge transport mechanism changes dramatically when transistor action begins. As C1 plus C2 approaches unity by one of the mechanisms described, many holes injected at J1 survive to be swept across J2 into P2. This helps to feed the recombination in P2 and to support the injection of holes into N2. Similarly, the transistor action of electrons injected at J3 and collected at J2 supplies electrons for N1. Obviously, the current through the device can be much larger once this mechanism begins. The transfer of injected carriers across J2 is regenerative, in that a greater supply of electrons to N1 allows greater injection of holes at J1 while maintaining space charge neutrality. This greater injection of holes further feeds P2 by transistor action, and the process continues to repeat itself. If C1 plus C2 is large enough, so that many electrons are collected in N1 and many holes are collected in P2, the depletion region at J2 begins to decrease. Finally, the reverse bias disappears across J2 and is replaced by a forward bias, in analogy with a transistor that is biased deep in saturation. When this occurs, the three small forward bias voltages appear as shown in Fig 1012b. Two of these voltages essentially cancel in the overall V, so that the forward voltage drop of the device from anode to cathode in the conducting state is not much greater than that of a single p-n junction. For Si, this forward drop is less than 1 V, until ohmic losses become important at high current levels. We have discussed the current transport mechanisms in the forward blocking and forward conducting states, but we have not indicated how switching is initiated from one state to the other. Basically, the requirement is that the carrier injection at J1 and J2 must somehow be increased so that significant transport of injected carriers across J2 occurs. Once this transport begins, the regenerative nature of the process takes over and switching is completed. Triggering mechanisms. The most common method of triggering a two-terminal PNPN is simply to raise the bias voltage to the peak value Vp. This type of voltage triggering results in a breakdown, or significant leakage, of the reverse biased junction. J2, the accompanying increase in current provides the injection at J1 and J3, as well as the transport required for switching to the conducting state. The breakdown mechanism commonly occurs by the combination of base width, narrowing and avalanche multiplication. When carrier multiplication occurs in J2, many electrons are swept into N1 and holes into P2. This process provides to these regions the majority carriers needed for increased injection by the emitter junctions. Because of transistor action, the full breakdown voltage of J2 need not be reached. As we showed in EQ 752, breakdown occurs in the collector junction of a transistor with IB equal 0 when MC equal 1. In the coupled transistor case of the PNPN diode, breakdown occurs at J2 when where MP is the hole multiplication factor and Mn is the multiplication factor for electrons. As the bias V increases in the forward blocking state, the depletion region about J2 spreads to accommodate the increased reverse bias on the center junction. This spreading means that the neutral base regions on either side, N1 and P2, become thinner. Since C1 and C2 increase as these base widths decrease, triggering can occur by the effect of base width narrowing. A true punch-through of the base regions is seldom required, since moderate narrowing of these regions can increase the alphas enough to cause switching. Furthermore, switching may be the result of a combination of avalanche multiplication and base width narrowing, along with possible leakage current through J2 at high voltage. From EQ 10.6, it is clear that, with avalanche multiplication present, the sum C1 plus C2 need not approach unity to initiate breakdown of J2. Once breakdown begins, the increased numbers of carriers in N1 and P2 drive the device to the forward conducting state by the regenerative process of coupled transistor action. As switching proceeds, the reverse bias is lost across J2 and the junction breakdown mechanisms are no longer active. Therefore, base narrowing and avalanche multiplication serve only to start the switching process. If a forward bias voltage is applied rapidly to the device, switching can occur by a mechanism commonly called dV/dt triggering. Basically, this type of triggering occurs as the depletion region of J2 adjusts to accommodate the increasing voltage. As the depletion width of J2 increases, electrons are removed from the N1 side, and holes are removed from the P2 side of the junction. For a slow increase in voltage, the resulting flow of electrons toward J1 and holes toward J3 does not constitute a significant current. If dV/dt is large, however, the rate of charge removal from each side of J2 can cause the current to increase significantly. In terms of the junction capacitance, Cj2, of the reverse biased junction, the transient current is given by where Vj2 is the instantaneous voltage across J2. This type of current flow is often called displacement current. The rate of change of Cj2 must be included in calculating current, since the capacitance varies with time as the depletion width changes. The increase in current due to a rapid rise in voltage can cause switching well below the steady-state triggering voltage Vp. Therefore, a dV/dt rating is usually specified along with Vp for PNPN diodes. Obviously, dV/dt triggering can be a disadvantage in circuits subjected to unpredictable voltage transients. The various triggering mechanisms discussed in this section apply to the two-terminal PNPN diode. As we shall see in the next section, the semiconductor-controlled rectifier is triggered by an external signal applied to a third terminal. The semiconductor-controlled rectifier, SCR, is useful in many applications, such as power switching and various control circuits. This device can handle currents from a few milliamperes to hundreds of amperes. Since it can be turned on externally, the semiconductor-controlled rectifier can be used to regulate the amount of power delivered to a load simply by passing current only during selected portions of the line cycle. A common example of this application is the light dimmer switch used in many homes. At a given setting of this switch, an SCR is turned on and off repetitively, such that all or only part of each power cycle is delivered to the lights. As a result, the light intensity can be varied continuously from full to dark. The same control principle can be applied to motors, heaters, and many other systems. We shall discuss this type of application next, after first establishing the fundamentals of device operation. The most important four-layer device in power circuit applications is the three-terminal semiconductor-controlled rectifier, Fig 1013. This device is similar to the PNPN diode, except that a third lead, gate, is attached to one of the base regions. When the semiconductor-controlled rectifier is biased in the forward blocking state, a small current supplied to the gate can initiate switching to the conducting state. Figure 1013. A semiconductor-controlled rectifier, A, four-layer geometry and common circuit symbols, B, current voltage characteristics. As a result, the anode switching voltage Vp decreases as the current Ig applied to the gate is increased, Fig 1013b. This type of turn-on control makes the SCR a useful and versatile device in switching and control circuits, Fig 1014. To visualize the gate triggering mechanism, let us assume that the device is in the forward blocking state, with a small saturation current flowing from anode to cathode. A positive gate current causes holes to flow from the gate into P2, the base of the NPN transistor. This added supply of holes and the accompanying injection of electrons from N2 into P2 initiates transistor action in the NPN. After a transit time Vt2, the electrons injected by J3 arrive at the center junction and are swept into N1, the base of the PNP. This causes an increase in hole injection of J1, and these holes diffuse across the base N1 in a transit time Vt1. Thus, after a delay time of approximately Vt1 plus Vt2, transistor action is established across the entire PNPN, and the device is driven into the forward conducting state. In most silicon-controlled rectifiers, the delay time is less than a few microseconds and the gate current required for turn-on is only a few milliamperes. Therefore, the semiconductor-controlled rectifier can be turned on by a very small amount of power in the gate circuit. On the other hand, the device current I can be many amperes, and the power controlled by the device may be very large. It is not necessary to maintain the gate current once the SCR switches to the conducting state. In fact, the gate essentially loses control of the device after regenerative transistor action is initiated. For most devices, a gate current pulse lasting a few microseconds is sufficient to ensure switching. Ratings of minimum gate pulse height and duration are generally provided for particular SCR devices. Turning off the silicon-controlled rectifier. Turning off the silicon-controlled rectifier, changing it from the conducting state to the blocking state, can be accomplished by reducing the current I below a critical value, called the holding current, required to maintain the C1 plus C2 equal 1 condition. Figure 1014 example of the use of an silicon-controlled rectifier to control the power delivered to a load. A. Schematic diagram of the circuit. B. Waveforms of the delivered signal and the phase variable trigger pulse. In some silicon-controlled rectifier devices, gate turnoff can be used to reduce the alpha sum below unity. For example, if the gate voltage is reversed in Fig 1014, holes are extracted from the P2 base region. If the rate of hole extraction by the gate is sufficient to remove the NPN transistor from saturation, the device turns off. However, there are often problems involving the lateral flow of current in P2 to the gate. Non-uniform biasing of J3 can result from the fact that the bias on this emitter junction varies with position when a lateral current flows. Therefore, silicon-controlled rectifier devices must be specifically designed for turn-off control. At best, this turn-off capability can be utilized only over a limited range for a given device. We saw in section 10.5 that the silicon-controlled rectifier has difficulty in efficiently turning off the device using the gate. We need to use additional circuitry to reduce the anode to cathode current below the holding current to change the SCR from the conducting state to the blocking state. This is, of course, clumsy and expensive. Hence, the insulated gate bipolar transistor IGBT was invented by Balaga in 1979 to address this issue. This variation on the SCR can easily be turned off from the conducting to the blocking state by the action of the gate. This device is also known by several other names, such as conductivity modulated FET, COMFET, insulated gate transistor, IGT, insulated gate rectifier, IGR, gain enhanced MOSFET, GEMFET, and bipolar FET, BiFET. Figure 1015 structure of an insulated gate bipolar transistor. The basic structure is shown for an N-channel device in Fig 1015. It combines an semiconductor-controlled rectifier with a MOSFET that is able to connect or disconnect the N+ cathode to the N base region, depending on the gate bias of the MOSFET. The MOSFET channel length is determined by the P region, which is formed by diffusion of the acceptors implanted in the same region as the N+ cathode. In other words, the channel length is determined not by the lithography of the gate, as in a conventional MOSFET, but rather by the diffusion of the acceptors. Such a MOSFET structure is known as a double diffused MOSFET, DMOS. The DMOS device is essentially an N-channel MOSFET. The main part of the IGBT is the N region, which acts as the drain of the double diffusion metal oxide semiconductor device. This is generally a thick, 50 micrometers, epitaxial region with a low doping, 100 trillions per cubic centimeter, grown on a heavily P+ at doped substrate that forms the anode. The N region can therefore support a large blocking voltage in the off state. In the on state, the conductivity of this lightly doped region is modulated, increased, by the electrons injected from the N+ cathode and the holes injected from the P+ anode, hence the alternative name conductivity modulated FET, COMFET. The increased conductivity allows the voltage drop across the device to be minimal in the on state. The current voltage characteristics are shown in Fig 1016. If the double diffusion metal oxide semiconductor gate voltage is 0, or below the threshold voltage, an N-type inversion region is not formed in the P-type channel region and the N+ cathode is not shorted to the N base. The structure then looks exactly like a conventional SCR that allows minimum current flow in either polarity until breakdown is reached. For positive anode to cathode bias VAK, avalanche breakdown occurs at the N, at P junction, while for negative VAK avalanche occurs at the N, at P plus junction. When a gate bias is applied to the double diffusion metal oxide semiconductor gate, we see that, for positive VAK, there is significant current flow, Fig 1017. The characteristics look like that of a MOSFET, with one difference: instead of the current starting to increase from the origin, there is an offset or cut-in voltage of 0.7 volts, as with a diode. The reason for this can be understood by looking at the equivalent circuit in Fig 1017a. For small VAK up to the offset voltage, the structure looks like a DMOS in series with a PIN diode made up of the P plus substrate, the anode, the N, blocking region, the base, which is essentially like an intrinsic region, and the N plus cathode. In this regime, there is negligible voltage drop across the DMOS device, and the PIN device is in forward bias. Figure 1016 output current voltage characteristics of an insulated gate bipolar transistor, N-channel. In this regime, there is negligible voltage drop across the double diffusion metal oxide semiconductor device, and the PIN device is in forward bias. The injected carriers from the anode and the cathode recombine in the N region. As we saw in Chapter 5, for a diode dominated by recombination in the depletion region, the current voltage characteristics show an exponential behavior, with a diode ideality factor of N equal to. Therefore, in this region, we get. On the other hand, when VAK is larger than the offset voltage, 0.7 volts, the characteristics look like that of a MOSFET, multiplied by a PNP bipolar junction transistor gain term. The equivalent circuit in this region is shown in Fig 1017b. In this regime, not all the injected carriers recombine in the near intrinsic N region. The current they supply, which is essentially the double diffusion MOSFET current IMOS, acts as the base current of the vertical PNP BJT formed between the P plus substrate, anode, the N, base, and the P, channel of the double diffusion metal oxide semiconductor device. Hence, the current is now given by Figure 1017 IGBT equivalent circuit, A, below the offset voltage, for low VAK, B, above the offset voltage, for high VAK. The shape of the characteristics looks like that of the double diffusion metal oxide semiconductor device. This is the preferred mode of operation of the IGBT. Finally, if the current levels are too high, the insulated gate bipolar transistor latches into a low impedance state like that of a conventional SCR in the on state. This is undesirable, because it means that the gate of the double diffusion metal oxide semiconductor device has now lost control. The insulated gate bipolar transistor clearly incorporates some of the best features of MOSFETs and BJTs. Like a MOSFET, it has high input impedance and low input capacitance. On the other hand, in the on state, it has low resistance and high current handling capability, like a BJT or an SCR. Because of these factors, and because it can turn off more easily than an SCR, the IGBT is gradually becoming the power device of choice, in place of the more traditional semiconductor-controlled rectifier. Nanotechnology is sometimes defined as engineered objects in the length scale of 1/100 nanometers with novel, useful properties. This nanoscale regime, sometimes also known as the mesoscale, lies between the microscale, microns, and atomic/molecular scale, 0.1 nanometers. When objects are shrunk from the macro to microscale and beyond, they don't just become smaller, but they also behave differently. One way to appreciate this is if one considers the fraction of atoms that lie at the surface of a sphere. For macroscopic or microscopic dimensions, the vast majority of the atoms are found to lie in the bulk of the sphere. As one enters the mesoscale, a substantial fraction of the atoms are found to be at the surface, which very often have different properties than bulk atoms. In other words, At some point smaller isn't just smaller but smaller is different. On the other hand, if one considers much smaller objects such as atoms/molecules, their properties belong to the realm of quantum mechanics and chemistry. Now, if one considers clusters of these atoms/molecules, as in a nanoscale object, because of collective effects between these atoms, new properties can emerge that are not manifested by the individual atoms. The physicist, Philip Anderson, eloquently described this as more is different. There are many nanoelectronic devices that are being investigated in research labs. We will briefly discuss a few interesting examples which show novel, nanoscale properties, according to the dimensionality of the nano device: zero-dimensional quantum dots, one-dimensional quantum wires and nanotubes, and two-dimensional layered crystals such as graphene. Many of the novel properties arise from the density of states of these low-dimensionality systems discussed in Appendix 4. Zero-dimensional quantum dots. Zero-dimensional quantum dot systems have singularities in the density of states, where n, e, varies as 1e. These are sometimes called artificial atoms. However, the analogy is not perfect. While atoms have a spherically symmetric Coulomb potential, V, R, 1/R, leading to energy levels that vary as 1 and 2 eq. 215, the confinement potential in quantum dots can be approximated as a paraboloic potential, reminiscent of simple harmonic oscillators, leading to equispaced eigenenergies in the quantum dot according to the rules of quantum mechanics. Quantum dot confinement also leads to an increase of the effective band gap, since the lowest eigenstates in the conduction and valence band are pushed up in energy, leading to an increasing blue shift, as dot sizes are reduced. This can lead to a dramatic change in the colors of quantum dots made of a certain semiconductor, simply by changing the dot size, with obvious applications in optoelectronics. For instance, one can incorporate such quantum dots in the active regions of lasers, and tune the emission wavelengths toward the blue, and sharpen the line widths compared to three-dimensional active regions. Quantum dots have also been used in solar cells to engineer the absorption characteristics of the cells, and match it better to the solar spectrum. Quantum dots can be made by so-called top-down approaches involving nanoscale lithography, followed by etching. Alternatively, bottom-up schemes such self-assembled quantum dots can be formed using heteroepitaxy. As described in Chapter 1, if we grow a dissimilar semiconductor on a substrate, if there is a lattice mismatch, it leads to strain in the epitaxial layer. Generally, the initial layers are smooth, which is known as the layer-by-layer Frank van der Merwe growth mode. As the layer becomes thicker, often there is roughening of the epitaxial layer because of increasing strain. This is known as the Volmer-Weber growth mode. If the lattice mismatch in the heteroepitaxial system is large, it can lead to very rough morphology or quantum dots forming on the surface of the substrate in a self-assembled fashion. This is known as the Stransky-Krastonov mode, and is the preferred mode of fabrication in many optoelectronic devices where precise location of the dots is not critical. This avoids time-consuming lithography and etching, and allows, for example, inclusion of quantum dots in the cavity of a laser to sharpen the emission line width. An interesting electronic application of quantum dots is in flash memories that we discussed in section 9.5.2. Recall that electrons can be stored in a non-volatile fashion in the floating gate of an metal oxide semiconductor structure, and the presence or absence of these electrons corresponds to digit bits 1 or 0. As one scales down the sizes of these flash memory cells, it would be desirable to scale down the thicknesses of the tunnel dielectric, in accordance with the scaling laws we discussed in section 6.5.9. However, one finds that if the tunnel oxide is less than 8 nanometers, there are inevitably manufacturing weak spots in the oxide which cause the stored electrons to leak away and not be retained for the requisite 10 years or longer. If the continuous floating gate electrode is replaced by an array of discontinuous quantum dots, and electrons are stored in them, we can more aggressively scale down the tunnel oxide, and therefore the memory cell. A weak spot in the tunnel dielectric might discharge electrons in a quantum dot in the vicinity of the weak spot, but the vast majority of the other dots which are electrically discontinuous would still retain the stored electrons. This greatly improves the reliability of the flash memory cells. One-dimensional quantum wires. One-dimensional semiconductor quantum wires or nanowires are an attractive platform for making ultra-scaled metal oxide semiconductor field effect transistors. These can be viewed as a natural evolution of the FinFETs or MUGFETs that we discussed in section 6.6.3. Recall that having a gate wrapped around three sides of a channel in a three-dimensional structure gives the gate better electrostatic control of the channel potential compared to a bulk MOSFET, and leads to better channel length scalability. In a nanowire MOSFET, the gate can be wrapped all around the channel, leading to even better gate control than in a FinFET. However, the drive current of an individual nanowire FET is generally low. Hence, one needs to make parallel arrays of these devices. Just as with quantum dots, such quantum wires can be formed by top-down lithography and etching techniques, or by novel bottom-up schemes. One such bottom-up scheme is known as the vapor-liquid-solid (VLS) approach, first developed by Wagner in the 1960s. In this scheme, one patterns metal catalysts such as gold to form quantum dots on a substrate. The structure is then loaded into a chemical vapor deposition system, and appropriate precursor gases are introduced, with the substrate at a high enough temperature that the gold metal catalysts melt. For example, to grow silicon nanowires, silane, silicon tetrahydride, is flowed in such that it dissolves in the molten gold catalyst dots. There is a supersaturation of silicon in the gold, leading to an extrusion of silicon atoms as single crystal silicon nanowires growing vertically on top of the silicon substrate, with the gold catalyst floating on top of the nanowire. At the end of the VLS growth, the gold catalysts can be etched off. Fortunately, due to the low solid solubility of gold in silicon, there is negligible gold contamination of the nanowires or the substrate. Vertical field effect transistors can be made in the forest of nanowires, or these nanowires can be harvested and subsequently laid down flat on another substrate for subsequent device processing. Other precursors such as germane for germanium nanowire growth, or 3,5 nanowires, can be grown by VLS. Another type of one-dimensional system is the carbon-based nanotube. As we saw in Chapter 1, carbon can be tetrahedrally bonded to four other nearest neighbor carbon atoms via sp3 bonding, leading to diamond. But carbon can also undergo sp2 bonding, which leads to a planar structure, such as the sheets of carbon atoms in graphite. This two-dimensional planar bonding arrangement of carbon led to the first nanostructures in carbon, based on so-called buckyballs or Fuller NS7. These are spherical shells of carbon atoms reminiscent of the quantum dots we described in the previous section. Fuller NS can be elongated into a tubular structure, leading to carbon nanotubes Fig 1018, and FETs can be made in them. These have somewhat similar properties as nanowire field effect transistors, but there are interesting differences in the density of states of these carbon-based materials. Figure 1018 nanostructures of carbon, A, two-dimensional graphene, B, one-dimensional nanotube, C, zero-dimensional buckyball, fullerene, D, linear band structure of graphene showing Dirac cones. For instance, depending on precise angular orientation of the carbon atoms in the cylindrical tube, which is known as the helicity or chirality of the nanotube, they behave as semiconductors, which are good for FETs, or metals, suitable for interconnects. Two-dimensional layered crystals. We have already met two-dimensional systems such as two-dimensional electron gases, 2DEG, in the inversion layer of a MOSFET made in a three-dimensional bulk crystal. Such quasi-two-dimensional systems are formed through electrostatic confinement. Recently, there have been breakthroughs in two-dimensional atomic crystals or layered materials. Staying with the theme of carbon, it was shown by Game and Novoselov in 2004 that one can peel off individual sheets of sp2, bonded carbon atoms from graphite, leading to two-dimensional atomic crystals called graphene. One can also view graphene as carbon nanotubes which are sliced along the axis of the cylinder, and flattened out into monoatomic sheets of carbon. The unit cell of graphene consists of a hexagonal array of carbon atoms with a unique linear band structure, E, K, shown in Fig 1018. This is obviously different from the parabolic E, K, relationship seen in most semiconductors. We saw in section 3.2.2 that the curvature of these parabolic bands determines effective mass of the electrons and holes. By contrast, the linear band structure in graphene is more reminiscent of the linear dispersion relationship of photons, which are known to have zero rest mass, and thus travel at the speed of light, c. The carriers in graphene, in analogy with photons, also have zero effective mass, and are known as massless Dirac fermions, traveling at a group velocity determined by the slope of the E, K, dispersion relationship discussed in section 1.5. The conical E, K, surfaces are known as Dirac cones. In graphene, electrons and holes travel at a so-called Fermi velocity, which is 10 times that of the saturation drift velocity in silicon or most semiconductors. Clearly, this makes graphene an attractive platform for very high-speed devices such as RF transistors. Unfortunately, one sees from the band structure in Fig 1018d, that there is no band gap between the valence and conduction band. Hence, MOSFETs in graphene have high off-state leakage currents for the reasons discussed in Chapter 6, making graphene FETs unsuitable for digital logic which demand high on-off ratio. This has led to interest in other two-dimensional layered materials which are similar to graphene, but have a band gap. One class of such materials are the transition metal dichalcogenides, TMDs. Transition elements include molybdenum, wolfram, etc., while chalcogens in the periodic table are column 4 elements such as sulfur, selenium, and tellurium. Transition metal dichalcogenides such as molybdenum sulfide have a hexagonal unit cell like graphene, and two-dimensional monoatomic sheet structure, but unlike graphene, have a band gap, making these materials attractive for short-channel metal oxide semiconductor field effect transistors. One could think of them as SWA scaled to the ultimate limit of atomic layer thicknesses. Yet another set of two-dimensional layered materials which have garnered interest recently are the topological insulators, titanium, such as the bismuth at selenide/telluride. This class of solids are insulating in the bulk, but have Dirac cone metallic surface states, similar to graphene, but with a novel twist. Remember that electrons have a quantum number called spin, which can have values of 1/2 corresponding to spin up or down. Normally, in most semiconductor devices we have equal populations of both spins. The spin simply adds a factor of 2 in the density of states, but otherwise can be ignored. When electrons orbit around a nucleus, they see an effective magnetic field due to the orbital motion, and spin up/down electrons can have slightly different energies in this magnetic field. The split-off bands shown in Fig 310 are the result of such interactions. On titanium surfaces such as bismuth selenide, due to strong spin-orbit interactions in heavy nuclei such as bismuth, the spin of the electron is locked orthogonally to the wave vector k, which determines its orbital motion. In other words, if electrons moving to the left on the titanium surface have spin up, electrons moving to the right will have spin down. Such intriguing physics may lead to novel nanoelectronic devices in the future which will not only exploit the charge of the electron, but also its spin, a nascent field dubbed spintronics, in analogy with electronics. Spintronic memory. Although spintronics based on semiconductors is a burgeoning field, spin-based ferromagnetic devices have been used for a long time in hard disks, and more recently in spin transfer torque random access memory, STTRAM. A brief discussion of ferromagnetism in solids is warranted to explain these devices. Spinning electrons can be thought of as tiny, atomic magnets which point up or down. Ferromagnetism is a magnetic state where a majority of the electron spins point one way or the other, even without an applied external magnetic field, which would tend to orient the electron spins. As we have mentioned in section 10.7.3, normally in solids spin up/down. Electrons are equally likely to be found, and the density of states has a factor of 2 spin degeneracy. We also saw in chapter 3 that electrons, being fermions, must have an overall wave function E, R, S, depending on position, R, and spin, S, that is antisymmetric. So, as shown in Fig 3.2, if the spatial part of the wave function is symmetric, the spins are antiparallel, and vice versa. So, in this case, since the symmetric, bonding, orbital is the lower energy state, it is energetically favorable for spins to be antiparallel, and the solid is not ferromagnetic. Such solids are paramagnetic, with no permanent magnetism. On the other hand, if free electrons are considered, which are not subjected to a strong ion core potential as in Fig 3.2, the antisymmetric orbital, with parallel spins, is energetically favorable because the electrons are further apart on average and, therefore, there is less Coulomb repulsion. Since the spins are parallel, it leads to ferromagnetism. So, what aligns the spinning electrons in a ferromagnet is electrostatic Coulomb interactions, rather than the much weaker magnetostatic interactions between the magnetic dipoles. This larger effective field is known as the Weiss exchange field, because it is driven by the antisymmetry of electron wave functions when two electrons are interchanged. As a result, in a ferromagnet, there is a higher of density of states of the majority spins near the Fermi level, Fig 1019a. Figure 1019a, spin-based memory. Depending on whether the free magnet on the right is parallel, antiparallel, to the fixed magnet on the left, we have a low, high, tunneling resistance corresponding to the two memory states. B. Phase change memory whose resistance changes depending on the crystallinity of the chalcogenide. This is the basis of a host of ferromagnetic spin-based memories. For example, one can have a permanent fixed ferromagnet that always points up, separated by a tunnel dielectric from a free magnet which can point up or down. If the two magnets are aligned, there is a high density of initial states and final states for majority spin electron tunneling near the Fermi level. This corresponds to a low tunnel resistance, and could correspond to bit 1. Spins do not flip during the tunneling process. On the other hand, if the free magnet is antiparallel to the fixed magnet, there is a mismatch between the initial and final density of states for both types of spin, and the tunnel resistance will be higher, corresponding to bit 0. This is known as tunnel magnetoresistance, TMR. This, and similar effects such as giant magnetoresistance, GMR, are used in hard disk memories that are ubiquitous in computers. These effects are also the basis of STT-RAMs, which offer a new type of universal memory that might one day supplant all the other types of memory that we discussed in Chapter 9, SRAM, DRAM, Flash. In STT-RAMs, to write a bit 1, a current flows through the fixed magnet, which spin polarizes the electrons along the majority spin direction. When an electron tunnels into the free magnet, it transfers spin angular momentum to the free magnet, applies a torque, and flips it to make it parallel to the fixed magnet. This sets the STT-RAM in the low resistance state, bit 1, during read operation. If the polarity of the right current is reversed, the sign of the angular momentum transfer to the free magnet is flipped, and it becomes antiparallel to the fixed magnet, setting it into the high resistance state, bit 0. Nanoelectronic resistive memory. As we saw for STT-RAMs, memory devices can be based on two resistance states, corresponding to digital bits 1 and 0. In some sense, such memory devices are simpler to make than logic transistors, where requirements, such as on-off ratios, etc., are much more stringent. In recent years, novel nonvolatile memories have been developed based on resistance changes. In resistive RAMs, ReRAMs, a dielectric such as high-K dielectric is sandwiched between two metal electrodes. Flowing a high right tunneling current through the dielectric can create defect trap states or charges in the dielectric, which can modify its resistance. The phenomena are akin to what we discussed in section 6.4.7 in the context of current voltage characteristics of silicon dioxide. The precise details of programming, called setting, and resetting, depend on the dielectric used in ReRAMs, and the physics is still somewhat controversial. In titanium oxide-based dielectrics, it is believed that the mechanism involves creation and annihilation of a string of oxygen vacancies, which results in a resistance change. Some dielectrics can be set and reset with unipolar pulses of different amplitude, whereas others require bipolar pulses of opposite polarity. Resistive RAMs are also known by a colorful name, memory resistor or memristor. Typical changes in resistance in ReRAM are several 100%. The challenge in these devices is demonstrating reliability in terms of repeated cycling between the two resistance states, without suffering from TDDB. Another type of resistive memory, where the resistance difference between states 0 and 1 is much higher than in ReRAM, factors of 100,000 are typical, is the phase change memory, PCM, Fig 1019b. Here the memory storage element is a glassy material, perhaps a chalcogenide such as germanium antimony telluride, GST. The passage of an electric current through a heating element such as titanium nitride is used to quickly heat and quench the GST, making it amorphous, which is a high resistance phase. Alternatively, it can be held in its crystallization temperature range for some time, thereby switching it to a low resistance crystalline state. Interestingly, phase change materials are not a new idea. They have been used extensively in rewritable RW compact discs, CDs, as the storage medium. A laser makes the layer amorphous, low reflectivity, or polycrystalline, high reflectivity, for optical storage of the digital bits. The field of nanoelectronics is still in its infancy. As the great Richard Feynman said, there is plenty of room at the bottom. Summary: 10.1 High frequencies in the microwave regime can be obtained by negative differential resistance achievable by tunneling, Esaki diodes, transferred electron effects, gun diodes, or transit time effects, IMPATT diodes. 10.2 High power switching is possible with PNPN diodes, thyristors, or SCRs. These devices can be understood in terms of two coupled BJTs. Similar effects in CMOS cause latch-up. 10.3 Modern power devices are based on the IGBT, which is a combination of an SCR and a MOSFET. 10.4 Nanoelectronics is based on the mesoscale between the larger, microscale, and smaller, atomic, dimensions where novel phenomena can be beneficially exploited.